Sir, we have started the streaming. We are live now.
Okay. So no one has joined. Okay. So let me wait until some students join online for this live session. Once they join, I will start discussing some of the questions that are posed by a few students. So no one has joined, I think. So until some students join, let me discuss some of the questions that were sent by students. Can you see the slides that I'm showing?
Not yet.
Okay, what is the problem? So I'm just sharing it. Open system setting. Entire scheme open. Why it's not? Devendra, can you help me?
Yes, sir.
Okay, it's not showing. I wanted to share PowerPoint.
So just open the PowerPoint and in Zoom, you just click on that share button.
Yeah, that's what I did.
Hmm.
There was some problem. Can you see me?
So yes, we can see you.
Yeah, so I've been sharing, I'm going there to share the entire screen. Share, okay. Now, what is that?
It is visible now, sir.
Now, sir, yes.
Screen is visible now? This PowerPoint is visible?
No, your PC screen is visible completely.
Yeah.
Yeah, sir, now your PowerPoint will come. Actually, it's little lagging behind, so it will come now.
Now?
Yes, sir. Now we
Okay.
can see.
Okay. So, yeah, there was a question about John Teller theorem. Okay, I shall tell you about that one. And, by definition, you all know what is John Teller distortion or John Teller theorem. If you consider an octahedral system and if EG orbitals are unsymmetrically filled, okay, in a better way, let me define that any nonlinear molecular system in a degenerate electronic state will be unstable and will undergo distortion to form a system of lower symmetry and lower energy, thereby removing the degeneracy. So this is more pronounced when we have EG orbital, okay, is unsymmetrically filled. For example, if you consider EG dx square minus y square and dz square, if these two orbitals are unsymmetrically filled, if you have one electron or three electron, then basically what happens, you come across John Teller distortion. And in John Teller distortion, you can see two type of John Teller distortion. Uh, First one is a general Jantel distortion, as I mentioned, that is pronounced with chromium 2. Okay, it has a D4 system, or any metal complexes having D4 electronic system, that's high field. In that case, one electron will be in EG, And similarly, D9 system, copper 2, there you will be having 3 electrons in EG. So in those cases, you call it as a common Jahn-Teller distortion. There is another term called second order Jahn-Teller distortion. What is that one? This occurs when the excited state of the transmetal has unequal occupation of d orbitals with identical energies. That means basically at room temperature, what would happen is you don't come across Jahn-Teller distortion in a system like, let's say, D4 system, low spin, or D5 low spin, or D6 low spin. In those cases, what happens? If you excite one of the electrons to EG orbital, then you'll be seeing unsymmetrical filling of EG. As a result, you come across Jahn-Teller distortion. This is called Jahn-Teller distortion, second order Jahn-Teller distortion, or pseudo Jahn-Teller distortion. So there is another called, okay, for example, I have shown some example, and all these examples, whatever I have shown, I have thoroughly discussed in my lecture. You can go back. And one more question was about the dynamic Jahn-Teller effect. And if you notice in the slide shown here, if, for example, if you take KCrF3, okay, in this one, you will see Jahn-Teller compression. So that means basically what happens when you have different type of cations, you can see temperature dependent distortions. For example, complex of the type, if you take M2PbCu NO2 6 times, where M is cesium, potassium, rubidium, or thallium, show temperature dependent Jahn-Teller distortion. For example, M equals cesium shows Z elongation below 285 Kelvin with complex ion adopting tetragonal symmetry, whereas for M equals K, where cation is potassium, distortion occur at below 273 K. Similar distortions were observed for, okay, rubidium at less than 276 Kelvin, and also in case of thallium at less than 245 Kelvin. So above these temperature, the molecules appear octahedral due to the dynamic Jahn-Teller distortion. So this is essentially dynamic, and rest whatever I said is static. And again, if you want to understand in a better way, I would say the molecule undergoes a permanent fixed change in shape that remains locked at room temperature. For example, D4 and D9, that's called static JT distortion, Jahn-Teller distortion, and that means molecules stay in one distorted shape under all normal conditions and temperatures. Okay, what is permanent bonds like? Do not change or flip. That means shorter bonds and longer bonds, whatever you come across in case of elongation, that doesn't change, or there is no flip flop between longer to the shorter. Okay, and then low symmetry shape is locked in place because energy barriers stop it from changing. Example, copper complexes like CuF2 means here it's octahedral. Okay, and then copper 2 show permanent elongation along the axis. This shows tetragonal elongation. And some cases where we come across tetragonal compression, in case due to the solid state effect, if a molecule assumes tetragonal compression, then packing may be very good. In that case, what happens? Density will be high, and if it is completely packed, thoroughly packed, with no scope for any voids, in that case, lattice energy will be very high, and molecule or ion attains stability. So in those circumstances, what happens? Although tetragonal elongation is preferred, tetragonal compression we do come across. So, dynamic Jahn-Teller distortion, the molecule rapidly flickers between the different shapes so fast that it looks permanently symmetrical on average. For example, what happens if you take D1 system, okay, and if the electron is excited and it can go to, elongation, and it can come back. So in those cases, you see these things. For example, if you take manganese oxide, this is high spin D4 Mn2O3. So the strong static distortion of manganese ion distorts the entire crystal lattice. This turns out should be a cubic structure into a permanently elongated tetragonal crystal structure. So this is nothing but the static Jahn-Teller distortion. Okay, and this is all about Jahn-Teller distortion. And then, okay, you can see here, I have shown the electronic configuration, also splitting of tetragonal elongation as well as tetragonal compression. And of course, that you already know. And in both the cases, for example, I have taken copper 2 plus here. In both the cases, what you have is D9 system. And in one case where you have 2 electrons in dz square and 1 electron in dx minus y square, that's tetragonal elongation. On the other hand, when you have 2 electrons in dx minus y square and 1 electron in dz square, that's called tetragonal compression. Nevertheless, both of them will show two transitions. For example, you can see here, okay, okay, yeah, so you can see here, in case of a typical Jahn-Teller distortion, you will see only one. Okay, without Jahn-Teller distortion, if you take D9 system, it shows only one hump. You know that D1, D4, D6, and D9 electronic configuration show only one DD transition. The similarities can be explained in this way: one electron, one less than half filled, one more than half filled, one less than completely filled. These four electronic configurations show single absorption. And similarly, D2, D3, D7, D8, where you have two electrons, two less than half filled, two more than half filled, and two less than completely filled. In these cases, we see three electronic transitions due to DD. So that means here, in case of D9 system, in absence of tetragonal distortion, it shows only one. But when tetragonal distortion happens, you come across two transitions that we call it as double hump pattern. Okay. So you can see here where this transition comes. You can see from the electron configuration and crystal field splitting I have shown in both the cases, irrespective of whether it's elongation or compression, you do come across two transitions in the form of double hump pattern. Okay, and okay, you can see this is how it appears. I hope it is clear for you people now. Okay, and now another question was there about isomerism. And of course, isomerism I have spelled out with all the examples and the different type of isomerism we come across in case of coordination compounds. Again, for your benefit, I am showing you here. You can see, yeah, you can see here, we have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different types of isomerism we come across. The simplest being ionization isomerism, where the primary valency switches. Okay, for example, in this one, primary valency is sulfate, and in the second one, primary valency is chloride. And now the sulfate becomes secondary valency and chlorine becomes primary valency. The switching of anionic ligands from primary valency to secondary valency is called ionization isomerism. And the second one is hydration isomerism. In that one, the number of hydrated molecules keep changing, but retaining the composition. Okay, that's about hydration isomerism. In case of linkage isomerism, I'm sure you are all familiar, where we have a ligand which has two donor atoms like nitrite. Okay, you can come across N coordination or O coordination. That's called linkage isomerism. And again, coordination isomerism, what we come across is two metal ions having two different type of ligands. If the ligands are switched between two metal centers, then that's called coordination isomerism. For example, tetramine platinum 2 plus and tetrachloropalladate 2 minus is there, that it becomes tetramine palladium 2 plus and tetrachloroplatinate 2 minus. And similarly, you can see hexamine cobalt 3 plus and hexacyanochromate 3 minus becomes, okay, hexamine chromium 3 plus and hexacyanocobalt 3 minus. That is called coordination isomerism. And again, coordination position isomerism you can see here. And here, what would happen? The metal oxygen state will switch, okay, in a bridging unit. Okay, for example, if you have a dinuclear system where two metal atoms are bridged by some ligands like oxygen or, okay, oxo, peroxo, or its amide, in that case, what happens? Okay, the switching of coordination oxidation state of the two metals, that's called coordination position isomerism. And then coordination polymerism. Coordination polymerism is something that you can see, example I have shown here. I have shown two several examples I have shown here. Diamino dichloroplatinum, and you can also see that is very similar to the a ionic complex such as tetramine platinum and tetrachloroplatinate. And similarly, you have PTNA3 thrice Cl whole twice and PTCl4. Okay, and another example is triamine trinitrito complex, and that also switches their coordination position. That's called coordination polymerism. And then conformation isomerism. In case of conformation isomerism, one can be tetrahedral, one can be square planar. Okay, usually nickel 2 complexes invariably show, because when you have relatively weaker ligands, okay, nickel can switch from tetrahedral to square planar, or it can have a combination of both in certain ratios. For example, if you see here, dark brown diamagnetic one shows square planar complex, whereas a dark green paramagnetic one will be having tetrahedral geometry. And another one is summation isomerism. You can see here summation isomerism. You have bromo, okay, ethylene amine, okay. So in that case, one has bromo, one has chloro is there, and whereas another ligand is chloro and bromo, they are switching their position. This is called summation isomerism. At the end, composition remains the same. And ligand isomerism, in this one, what happens? Let us say there is a N-propylamine is a ligand in one, in another one isopropylamine is there. And of course, N-propylamine and isopropylamine have the same composition. So this is called ligand isomerism. And then valence isomerism is also there. And again, spin isomerism also we come across. The spin isomerism arises due to the temperature dependence of some of the metal complexes. So that means with temperature, they become high spin, or high spin can become low spin. Okay, this is spin isomerism. These are all the isomerism we come across among coordination compounds. And if you have any other what is similar in coordination polymerism? Okay, you can see here in case of coordination polymerism, you see, for example, you see, diamino dichloroplatinum is very similar to the combination of tetramino platinum, okay, and tetrachloroplatinate. If you see overall, if you take this one, 2 platinums are there and 4 amines are there, and then 4 chlorides are there. If you divide it by 2, this will be very similar to this one. Okay, that is called coordination polymerism. Hope you have understood now. For example, if you take again this one also, here if you see 2 platinums are there, and then 6, okay, 4, okay, and okay, here this is a dimer if you there. Okay, this is platinum, okay, Na3 thrice Cl twice and PtCl4. That means basically what happens, the ratio of ligands with respect to one metal will remain same. Okay, this is called coordination polymer. Same thing is true in case of this cobalt also. If you see here, for example, triamine, trinitrito, nitro, cobalt is there. And then here, this is a combination of two. One is hexamine, okay, cationic compound, 3 plus, and then hexanitrito or nitro cobalt. And then again, if you take it, per cobalt, you can see 3 amines and 3 nitrate. Or per cobalt, you can see 6 NO2 or 6 NH3. Okay, that means at the end, ratio of different type of ligands with respect to the metal retains the same. Hope it is clear for you now, Rose. Why does the distortion stop happening at certain temperature? Okay, well, you know, probably at a particular temperature it gets stabilized. That is the reason. Okay, and if you heat it further, it may come back to the original. Okay. Yeah. So any other question? There is another question about palladium. Okay, why palladium is good for CH activation. Of course, if you look into most of the catalytic reactions under homogeneous catalysis carried by transition metals, invariably you come across palladium, and among palladium, we come across many type of palladium complexes, palladium acetate, okay, and tetra, kiss triphenyl phosphoropalladium, palladium DBA thrice, or dichloro amino platinum, or dichloro triphenyl phosphine platinum. So in most of these cases, okay, palladium is there, not platinum. Palladium is there. And one interesting thing about palladium is it is a 4D element, okay? And 4D and 5D elements are better suited for homogeneous catalysis just because the intermediates have very stable crystal stabilization energy. You know that crystal stabilization energy increases when you go from 3D to 4D to 5D. So that is one thing. And another one is, interesting thing about palladium is palladium can show three different oxygen states, 0, 1, and 2. And also it can show two oxygen states with a difference, two stable oxygen states with a difference of 2 electrons. In fact, we have shown examples in case of Ghazal's research work. Okay, Ghazal is here, she is a TA. And in her research work, we have also shown and isolated palladium 0, palladium, not palladium 0, palladium 1, palladium 2, and palladium 3, and of course palladium 4. So basically what happens, since it can show stable 4 different type of oxidation, and we come across 2 stable oxidation states with a difference of 2 electrons, that is a important criterion in performing homogeneous catalysis, where we come across two important reactions such as oxidative addition and reductive elimination. And another thing is, many of the metal to carbon bonds are very stable with respect to the palladium. That's one thing. That means in homogeneous catalysis, we come across many times formation of metal to carbon bond, 1 or 2 carbon bonds, and especially 2 carbon bonds will be formed in a cis disposition. And at the end, during reductive elimination, we can see concerted elimination. Okay, 3-bond concerted elimination. And also, in case if there is a trans addition is there, palladium shows isomerism, reasonably low temperature to convert trans into cis. If 2 carbon atoms are at trans position, okay, there you cannot expect concerted elimination. In order to have concerted elimination, that complex should undergo isomerism from trans to cis prior to reductive elimination, so that they come very close, okay, to each other. When the two ligands or 2 carbon fragments come very close to each other, what happens? They can start interacting and CC bond formation starts, and this can be eliminated. Okay, so this facilitates. And also this can readily form bonds with oxygen, nitrogen, sulfur, and also olefins. It has a high affinity for pi bond formation also, and also pi complex such as olefins, ethylene, and all those things. That's the reason this is well suited for CH activation, not only CH activation, even hydrogenation and many other organic transformations. Okay. And of course, you said it is expensive. Certainly, it is expensive. Nowadays, it's more expensive. But on the other hand, if you do reactions carefully, and at the end of the reaction, if we collect all the aliquot and share it, and we can recover palladium from that one. All palladium waste, you take it, collect it. Once you collected sufficient amount of palladium waste, then you take that one, add aqua regia. When you add aqua regia, matter dissolves, and all organic uh, compounds in it will float. Then you do filter. Once you filter, the clear solution will be having only palladium. And then on steam bath, if you remove everything, you end up getting palladium nitrate. And palladium nitrate with concentrated chloric acid or nitric acid, you can convert into either chlorides or nitrate. Once you convert chlorides or nitrates, generation of various substituted compounds such as palladium chloride, palladium acetate, Pd2DBA thrice, or palladium tetra, palladium potassium, tetrachloropalladate, or palladic acid. Everything is very easy. These are the starting materials for making many precursors which are used as catalysts in homogeneous catalysis. Hope is it clear for you people, right? Is it clear? why palladium? And of course, it's very challenging to use nickel too, because by virtue of being in 3D, okay, it has a less crystal field stabilization energy, and as a result, and as a result, it has some limitations. Nevertheless, we can manipulate electronic situation at nickel by using different interesting ligand systems, and hence we can make it as good as palladium, and we have done in our group as well. Is that clear? I do not know who asked that question, and I hope that person who asked the question about palladium is present here. Any other question? I hope you are, what I would say is, please listen to talk completely. And then I have shown a lot of worked examples. Yeah. Okay. I have shown a lot of worked examples, and go through those things, and also try to find out similar problems in textbooks and study so that you can do well in your exams. Any question? Why do organic reactions transition state do not emit light? Okay, what does it mean? No. I mean, it's not, but the question is not clear to me. You're talking about fluorescence and phosphorescence? Or you're talking about OLEDs, organic light emitting diodes? Okay. I think the question you asked about phosphorescence, right? If any reaction, okay, in any organic reaction, okay, if there is a transition, okay, if that, in the electronic transition that happens, okay, if the transition state, okay, it is, okay, if the electronic transmissions are in a simple way, if I say it's short-lived, okay, if it is short-lived, okay, in that case you will not see the energy that is converting, okay. It's very similar to the spin lattice and spin relaxation that we come across in NMR. Okay, the way we have NMR time scale, we also have time scale here. Okay, if the time scale that is much faster than 10 to the power minus 14 seconds, any transition. Okay, so then basically such organic reactions do not emit light. Okay, so in order to see light emission in a typical organic reaction, it should be last for more than 10 to the power minus 14 seconds. Let's say 10 to the power minus 8 seconds or 10 to the power minus 6 seconds. Okay, in that case, what happens? You can anticipate. Okay, unfortunately, many organic reactions exceed that, okay, duration, and it will be much faster than 10 to the power minus 14 seconds. As a result, probably you don't see light emission in an organic reaction. Yes, if you slow down the transition, okay, uh, okay, and if the transition state, okay, if photon stays for a while, okay, and probably you have to slow down the transition state, okay, yes. Why does it require to be 10? Well, you see, every system has a time scale. For example, if you want to see electronic transition, that will be around 10 to the power minus 14. If you want to see NMR time scale, that is 10 to the power minus 8 second. Okay, if any dynamic process is there, okay, that is faster than 10 to the power minus 8, that is the limitation we come across. Okay, so in that case, what happens? You don't see NMR, you will see a broad peak. Okay, so that means the sufficient amount of time, okay, when a nucleus is excited to the excited state, it should stay there. And if it comes back much faster than 10 power minus 8, normally you don't see it. So basically there's the limitation of any system. Okay, that's the reason, that is it. So when a particular transition state, okay, if it has to emit light, okay, there should be formation of photon. Okay, for that one there should be enough energy should be there, and that, okay, energy should come when the activation energy spares molecular vibrations. In that case, you can come across, okay, uh, formation of a photon, and then hence you should be able to see light unless it converts into a photon. So this is not sufficient. 10 to the power minus 14 seconds is not about sufficient energy, we have to convert that. Any other questions? So any other questions? Okay, probably next month I will be, planning for one more live session. Rose, if you have more questions, please do share, or you can come up with those questions. We'll try to clarify your doubts. Okay. All the best to you. So if no more questions, and probably we can close the session, I think. Yeah, please close the session then. Thank you all.
Hello, sir. Should we stop the session?
Yeah, please. Yeah.
Okay. Thank you, sir.
Okay. Thank you. Yeah. Okay, Ghazal.
Okay, sir.
Yeah. Yeah, I didn't get immediately what